Welcome to the deep dive. We are truly living through an incredible moment in technology where artificial intelligence, particularly large language models or LLMs, are reshaping industries, from creative content generation to powering customer support. These powerful AI brains are doing things we once only dreamed of. But here's the key, the differentiator that makes a general purpose LLM truly yours: fine tuning. Today, we're embarking on a deep dive into the ultimate guide to fine-tuning LLMs from basics to breakthroughs, a comprehensive report from CIADAR, Ireland's Center for AI. Our mission is to distill this robust technical work into actionable insights, surprise hot facts, and clear explanations, all designed to make you genuinely well-informed on this rapidly evolving field. Think of it like this. A pre-trained LLM is like a master chef, incredibly skilled in general cuisine. Fine-tuning, however, is like teaching that chef to perfectly master a very specific niche style of cooking that caters precisely to your restaurant's unique menu.
Yeah, that's a great analogy. And what's truly fascinating here is how this report emphasizes not just what LLM fine-tuning is, but the intricate how and the critical why behind successful implementations. Looking back, large language models represent a monumental leap from earlier natural language processing models. Historically, our AI systems struggled with context over long sentences or understanding nuances. LLMs, with their vast scale, have fundamentally changed that. They leverage innovations like the self-attention mechanism within transformer architectures. This allows them to efficiently process vast amounts of text, understanding long-range dependencies and vastly improving coherence and context in their responses. Another pivotal development has been reinforcement learning from human feedback, or RLHF.
Right, RLHF. That's about aligning the AI more closely with what humans want.
Exactly. It refines models based on actual human preferences and responses, aligning them more closely with our commands and values. And this comprehensive guide from CEDAR meticulously breaks down the entire fine-tuning journey into a structured 7-stage pipeline. It uses a clear roadmap from beginning to end.
That roadmap is exactly what we need, because before we even begin our journey through the stages of fine-tuning, there's a crucial distinction that can often be confusing. We need to clarify the two primary approaches for adapting an LLM to your specific data or tasks: fine-tuning versus retrieval-augmented generation, or RG. Why is it so important for you, our listener, to understand this difference, and when would you choose one over the other for your AI application?
That's an excellent question, and it's truly foundational for anyone looking to leverage LLMs effectively. Let's start with retrieval-augmented generation, or RV. Imagine you have a vast, constantly updated library of your company's internal documents, detailed product manuals, or evolving HR policies. RG allows an LLM to access and intelligently utilize that specific up-to-the-minute information without having to be retrained on it, which is a huge advantage.
Okay, so how does it actually work?
Here's the high-level process. When you submit a query, that query first goes through a smart search in a specialized database, often a vector database that holds your private data. The system retrieves the most relevant snippets of information.
Based on the query, yeah.
Based on the query's meaning, yeah. It uses those snippets as additional context. This enriched prompt, now containing highly specific and current information, is then sent to the LLM. The LLM uses this new context to generate its response, grounding its answer in your verifiable data. This entire pipeline avoids the extensive costs and time associated with directly altering the LLM's core knowledge base.
So it's like the LLM is a brilliant general-purpose expert, and RA is equipping that expert with a very specific up-to-the-minute library to reference just before they answer a question, rather than trying to rewrite the expert's entire foundational knowledge.
Exactly. You nailed it. The practical benefits are substantial. RA delivers up-to-date and accurate responses because it's pulling from your most current data. This significantly helps in reducing inaccurate responses, what we commonly call hallucinations, because the output is grounded in verifiable, relevant knowledge from your sources.
Right, it has something to point back to.
Precisely. You get truly domain-specific responses tailored to your proprietary data, which is invaluable for internal business applications. Plus, it offers remarkable efficiency and cost-effectiveness because you're avoiding the very time-consuming and expensive process of fine-tuning the base model itself.
Makes sense. What are some common use cases?
Oh, things like question-answering chatbots for company documents, augmenting search engines with LLM-generated answers, and building knowledge engines for internal functions like HR or compliance. Really useful stuff. Now let's look at fine-tuning. While RAG is about providing context, fine-tuning is about changing the model itself.
Okay, changing its core.
Yeah. It adjusts the LLM's underlying behavior, its distinctive writing style, or deeply embeds new domain-specific knowledge by actually updating the model's parameters using a specialized data set. You typically choose fine-tuning when you need the model to fundamentally change how it acts, or to adopt a very specific tone, or when you need it to deeply internalize new knowledge so it becomes part of its core reasoning, not just external lookup.
So RAG is like giving it notes, fine-tuning is like sending it back to school for a specific subject.
That's a good way to put it. And a key difference in terms of transparency is that RGA systems can generally point to the specific documents they retrieve to form an answer, which often isn't possible with models that are solely fine-tuned, as their knowledge is sort of baked in, internally assimilated.
So what does this all mean for you, our listener, if you're thinking about building your own AI application? Is it just a one or the other choice, or are there scenarios where you combine them?
That's the real insight here. The strategic choice truly depends on what you need the AI to achieve with information. If the primary need is to access external, frequently updated data like a dynamic Q&A system pulling from a live knowledge base, then ARG is often the superior option.
Got it. External data access dash RAG.
Right. However, if your goal is deep model adaptation, meaning you want to fundamentally change the model's behavior, its stylistic output, or deeply embed domain knowledge for tasks like summarization, where the model needs to truly understand and rephrase content in a specific way, then fine-tuning is typically better.
Changing the model itself, fine-tuning.
Exactly. But for many complex real-world scenarios, such as a customer support automation system that needs both up-to-date information and to maintain a specific empathetic tone.
Ah, okay, like combining both needs.
Precisely. In those cases, a hybrid approach combining fine-tuning and RBIGs is often optimal. This allows you to get the best of both worlds, a model that behaves exactly how you want it to, while also having access to the most current information.
That's a powerful distinction. So it's not a simple choice, but a strategic one based on the AI's core mission. And speaking of strategy, the report lays out a comprehensive journey for fine-tuning, breaking it down into what it calls 7 distinct stages. This is our roadmap for the rest of our deep dive, showing how we get from a general-purpose LLM to a finely tuned specialist.
Absolutely. And each of these 7 stages is crucial for achieving optimal performance and ensuring the fine-tuned model behaves as intended. You really can't skip steps. They are: first, dataset preparation, which truly sets the foundation. Second, model initialization, where you select and load your pre-trained model. Third, training environment setup, getting all your hardware and software ready.
The nuts and bolts.
The nuts and bolts, yeah. Fourth, the actual fine-tuning process itself. Fifth, evaluation and validation to check if it's good enough. Sixth, deployment, bringing the LLM to life. And finally, seventh, monitoring and maintenance for its ongoing performance and reliability. Skipping any of these can lead to suboptimal results or even critical failures down the line. Let's begin with stage 1. Data preparation. This is arguably the most critical stage because, simply put, the model is only as good as the data it learns from. High-quality data is paramount.
Garbage in, garbage out, as they say.
Exactly. So first is data collection. This involves gathering data from a diverse range of sources. Think CSV files, web pages, SQL databases, even stuff stored in S3 buckets. The report mentions specific Python libraries that help here, like Pandas for structured data, Beautiful Soup for web scraping, School Alchemy for databases, Boto 3 for AWS S3, tools to make collection efficient.
Okay, so you've gathered all this raw data. What's next?
Next is data preprocessing and formatting. Raw data is almost never ready to use. This step is crucial for transforming it into high-quality input. It involves cleaning the data, removing noise, errors, inconsistencies, handling missing values, and formatting everything to match the specific requirements of your fine-tuning task.
Like getting it into the right shape for the model.
Precisely. For text data, this includes steps like tokenization.
Breaking text into words or pieces of words.
Yes. And lemmatization, which reduces words to their base or dictionary form, helps the model generalize better. The report mentions tools like Spacey, NLTK, and the Hugging Face datasets library for this. A common challenge, especially with real-world data, is handling data imbalance.
Meaning you have way more examples of one thing than another.
Exactly. This is vital to ensure balanced performance across all categories in your dataset, preventing the model from just ignoring the less frequent but potentially important examples, the minority classes. There are techniques like oversampling, where you create synthetic examples of the underrepresented categories. SO is a popular method for this, using libraries like imbalanced learn.
Or you could just remove some of the majority examples.
Right, that's undersampling. You can also adjust how the model learns during training, maybe by giving more weight to the underrepresented categories in the loss function, or using techniques like focal loss. It's also crucial, when dealing with imbalance, to use appropriate evaluation metrics beyond just accuracy. Things like precision recall AUC, F1 score, Cohen's kappa give a much better picture.
Okay, data's clean, balanced. Now what?
Then, you need to split your dataset. A typical approach is to set aside a portion, say 80%, for training the model, and maybe 10–20% for validation.
And the validation set is for checking how well it's learning on data it hasn't seen during training.
Exactly. It gives you an honest assessment of how well it generalizes. There are different ways to split. Simple random sampling, stratified sampling to keep proportions right, or more complex methods like k-fold cross-validation. Tools like Sklern.model selection handle this. For many supervised learning tasks, data annotation is essential. This is the process of labeling or tagging your data.
Like telling the model, this email is spam or this sentence has positive sentiment.
Precisely. Approaches range from human annotation, which is the gold standard for accuracy but can be slow and expensive. Tools like Prodigy can help here. Then there's semi-automatic annotation, using machine learning to help humans, like Snorkel with weak supervision. And fully automatic annotation, which is scalable, but, accuracy can sometimes be a concern. Amazon SageMaker Ground Truth offers options here.
What if you just don't have enough data to begin with?
That's where data augmentation DA comes in. It's about artificially expanding your training data sets to address scarcity and improve model robustness. For text, this might involve using word embeddings like Word2Vec or Glove to find synonyms, or using back translation, translate to another language and back again, using something like the Google Translate API to get paraphrased versions.
Liver.
Yeah. There are also libraries like Text Attack for generating adversarial examples, or NLP-AUG, that offer various techniques. And a really interesting recent development is synthetic data generation using LLMs themselves.
Using an AI to create training data for another AI.
Kind of, yeah. You can use powerful LLMs like GPT-3 or 4 to generate new data samples by carefully crafting prompts. But, and this is a critical caveat highlighted in the report, you absolutely must verify the accuracy and relevance of any synthetic data generated by LLMs before using it. It can be noisy or subtly wrong. Careful oversight is key.
Sounds like data preparation is a minefield of potential issues.
It can be. The report lists several challenges in data preparation. Ensuring domain relevance is huge mismatched data, leads to poor generalization. Data diversity is crucial to prevent biases. Data size you need enough, often 1,000 plus samples recommended, but huge data sets bring storage and compute challenges. Data cleaning and preprocessing, we talked about noise degrades performance. Data annotation needs precision. Handling rare cases adequately is important for generalization. And of course, ethical considerations scrutinizing data for harmful or biased content, ensuring privacy, it's a massive responsibility.
This sounds incredibly crucial. It's like we're preparing the model to see the world through a carefully curated lens. But if that lens is dirty or distorted, the model's vision will be too. All that meticulous work in data preparation sounds like a huge undertaking. But once the data is prepped, we move on to stages 2 and 3, model initialization and training environment setup. What does that entail to get our LLM ready to learn?
You're right, it's a monumental first step. But without it, the rest crumbles. Stages 2 and 3 are about preparing the LLM for the actual training process. This involves a series of critical steps. You first set up your computational environment. This usually means getting access to powerful hardware like GPUs.
Graphics cards, but super-powered ones for AI.
Exactly. Or specialized AI chips like TPUs. These are essential for accelerating deep learning computations. Then you install all the necessary software dependencies, Python libraries, frameworks like PyTorch or TensorFlow, using package managers like pip or conda. Next, you choose your pre-trained language model. This could be a big, powerful one like Llama 3 70B, or maybe something smaller and more efficient like Hugging Face's Phi 3 Mini, depending on your needs and resources.
So you download this base model.
Yep, you download and load that model into memory, ensuring its underlying structure is initialized and ready. Only then can you actually execute your fine-tuning tasks. When it comes to key considerations in this setup, privacy is a big one. Many businesses, understandably, prefer not to share their sensitive data with external LLM providers.
Right, you don't want your confidential company data going to OpenAI or Google necessarily.
Exactly. So in such cases, hosting an LLM on local servers or using models available through private cloud providers ensures data remains within the company's control. This ties directly into cost and maintenance. Hosting on-premises requires a significant upfront investment in hardware and ongoing IT effort, but you get full control. Cloud vendors, on the other hand, handle the infrastructure maintenance, but operate on monthly billing, typically based on model size and usage. It offers flexibility but less direct control and potentially ongoing costs.
Yeah, the hardware and software need to play nicely together.
Absolutely. For hardware, powerful GPUs like NVIDIA's A100 or V100 are commonly mentioned, along with Google Cloud TPUs. For software, you need deep learning frameworks like PyTorch or TensorFlow that are compatible with your chosen hardware and model. A crucial aspect of training setup is selecting the right optimizers. These are the algorithms that dictate how the model actually learns and adjusts its parameters during training.
How it optimizes its learning.
Pretty much. Think of optimizers as different strategies for finding the best model settings. Some, like stochastic gradient descent, SGD, are simple and memory efficient but can be sensitive. Mini-batch gradient descent strikes a balance, used very commonly. Then you have adaptive optimizers like AdaGrad, RMSProp, and AdaDelta, which adjust the learning rate for each parameter individually. They can be great for certain types of data or problems like sparse text data or recurrent networks.
So choosing the optimizer isn't trivial.
Not at all. It's a strategic decision that fundamentally shapes how efficiently and effectively your LLM learns from your unique data. It's like picking the right gear for a specific type of terrain, as the report implies.
What are the common pitfalls here in the setup stage?
Challenges in training setup often include ensuring compatibility between hardware and software versions that can be a real headache, managing all the software dependencies correctly, and critically, choosing the correct loss function, the mathematical formula used to measure how well the model is doing, which guides the optimizer.
Okay, so how do we avoid these pitfalls? What are the best practices?
The report outlines several best practices. Using an optimal learning rate, typically a small value, maybe with a schedule that decreases it over time, helps stabilize learning. Batch size considerations. Balancing memory limits with efficiency. Smaller batches might need less RAM but can be noisy. Larger batches are more stable but need more memory. Saving checkpoints regularly. Periodically saving the model's state during training. This is crucial. You often pair this with early stopping halt training if the performance on the validation set starts getting worse to prevent overfitting.
Saving your progress, essentially.
Exactly. Hyperparameter tuning. Using tools like Optuna, HyperOpt, or RateTune to automatically find the best settings for things like learning rate, batch size, etc. saves a lot of manual effort. For really big models, using data parallelism and model parallelism. Distributing the training workload across multiple GPUs or machines using tools like Horovod or DeepSpeed.
Makes sense for huge models.
Regular monitoring and logging. Using tools like TensorBoard, weights and biases, or MLflow to watch the training process in real time. Help spot issues early, actively handling overfitting and underfitting. Using techniques like L2 regularization, dropout, or more data augmentation if needed. Considering mixed precision training. Using a mix of 16-bit and 32-bit numbers to speed up training and reduce memory use, often without losing much accuracy. And finally, documentation and reproducibility. Meticulously recording everything, hardware, software versions, configurations, data used, essential for debugging, collaboration, and future work.
That's a lot to consider. It's truly like setting up a high-performance race car. You need the right engine, the right fuel, and you need to monitor every dial engaged to ensure it performs at its peak without overheating. Now, with all that meticulous preparation done, we arrive at stage 4, the actual fine-tuning. This is where the real transformation takes place.
Indeed, this is where the model truly adapts to your specific task and data. It's where the learning happens. Fine-tuning can come in a couple of forms, partial or full fine-tuning. Full fine-tuning involves updating all of the model's parameters, billions of them potentially.
Which sounds computationally very expensive.
It absolutely is, but it offers the most comprehensive adaptation. Alternatively, there are approaches grouped under parameter-efficient fine-tuning, or PE-FIFT. These methods involve things like attaching additional smaller layers to the pre-trained model and only updating these new layers, or maybe updating just a small subset of the original parameters.
So you're not touching the whole giant brain, just specific parts.
Exactly. This significantly reduces computational requirements, the memory footprint, and can also help mitigate overfitting, where the model just memorizes the training data. The strategic insight here is that you don't always need to retrain the entire immense model. Sometimes a more surgical approach is far more efficient and effective. One of the most impactful and widely used PE-FIG techniques is low-rank adaptation, or LoRA.
LoRA, right. Heard a lot about this one. How does it work, basically?
Okay, LoRA. It's quite ingenious. It essentially freezes the original massive LLM weights. They don't change during fine-tuning. Instead, it applies the changes, the updates, to a separate, much smaller set of weights, specifically low-rank matrices that are then subtly integrated, often added, to the original parameters during the training process.
So the changes are stored in these small matrices.
Exactly. This dramatically reduces the number of trainable parameters. We're talking maybe less than 1% of the original model size sometimes. This speeds up the fine-tuning process enormously and drastically lowers the memory and compute costs. The benefits are clear. Reduced computational load, a smaller memory footprint, incredible flexibility because it can be easily layered onto existing models, and it's compatible with other fine-tuning techniques.
And you mentioned it's good for multiple clients.
Yes, it's particularly useful when you have multiple clients or use cases, each needing a distinct fine-tuned model. You can create specific LoRa adapters for each one without having to store multiple copies of the entire huge Bose model. You just store the small adapters. Building on LoRa, the report discusses weight-decomposed low-rank adaptation, or DORA.
Okay, Dora. An improvement on Laura.
It seems so. DORA improves upon LoRa by decomposing the weight changes into two components: magnitude, how strong the change is, and direction, which way it points, essentially. It then adapts both of these components. This apparently subtle change leads to consistently superior performance compared to LoRa across a wide range of tasks, including language processing and even visual understanding tasks.
And does it add complexity, make things slower?
That's the impressive part. The report states it achieves this enhanced performance without introducing any additional inference latency. So it keeps the model efficient when it's actually being used. Another architectural innovation gaining significant traction is mixture of experts, or MOE.
Mixture of experts sounds like a committee.
Kind of. The concept behind MOE is to divide the computation within a layer of the neural network into several specialized subnetworks, called experts. Each expert processes the input, and then the results are combined, often selectively. This can be dense, where every expert is engaged for every input, or sparse, where only a subset of experts is utilized for any given input token. Sparse MO, SMOE, is particularly interesting for efficiency,
Why sparse?
because you get the power as a huge model, all the experts combined, but the computational cost of a much smaller model at inference time, since only a few experts are active for each token. A prime example highlighted is Mixtral 8x7b. It uses a sparse mixture of experts architecture. It basically has the structure of Mistral 7b model, but each relevant layer incorporates 8 specialized feed-forward blocks, the experts.
8 experts per layer. Wow!
Yeah. And for every input token, a router network dynamically selects 2 of those 8 experts to process the current state and combine their outputs. So, while the overall model architecture contains parameters equivalent to a much larger, dense model, around 47 billion effectively, each input token only actively uses the parameters of the 2 selected experts plus the shared parts of the model, about 13 billion active parameters during inference.
So it feels like a huge model, but runs much faster.
Exactly. This makes it incredibly efficient. Mixtral 8x7b has shown remarkable performance, matching or even surpassing larger models like Llama 270b and GPT 3.5 on various benchmarks, excelling notably in mathematics, code generation, and multilingual tasks. This also highlights how model specialization is becoming key. Some models like GPT-4o or Llama 3 are great general assistants, while others like WizardLM might be better proposers in specific workflows, different architectures, different strengths. Beyond structural modifications, reinforcement learning for fine-tuning is a powerful paradigm for aligning LLMs with human preferences, getting them to behave how we want.
This is where RLHF comes in again.
Yes, RLHF is a major application. And a key algorithm used within RLHF is proximal policy optimization, PPO. PPO is a policy gradient method. It helps the LLM learn to produce outputs that humans prefer based on feedback. In the typical RLHF setup, Figure 6.11 in the report shows this, PPO adjusts the LLM's policy, its way of generating text, based on rewards provided by a separate reward model. And that reward model itself is fine-tuned using human feedback, humans ranking different AI responses. Hugging Face's TRL library includes tools like PPO Trainer for this.
Sounds complex. Reward models, PPO training.
It can be complex to set up and tune properly, which leads to direct preference optimization, DPO. DPO offers a more streamlined approach. It aims to align LLMs with human preferences directly, bypassing the complexity of training a separate reward model in RLHF.
How does it do that?
It optimizes the LLM using a simple classification objective based directly on preference data pairs, responses where one is marked as preferred over the other. It essentially increases the likelihood of the model generating the preferred responses. It's often simpler to implement and tune than PPO.
So DPO is just better. simpler and effective?
Well, there's an interesting discussion in the source about the PPO versus DPO debate. Some research suggests DPO might sometimes exploit loopholes or be sensitive to shifts in data distribution, whereas PPO, when configured optimally with things like advantage normalization, large batch sizes has demonstrated robust effectiveness, even surpassing powerful models on challenging tasks like code generation in some studies. So the best approach might depend on the specific context.
Not a settled debate, then.
Not entirely, it seems. And there are even newer methods emerging, like odds ratio preference optimization, or RPO. RPO is novel because it adds a specific loss term based on odds ratios. This not only encourages desired generations like standard fine-tuning SFT or DPO, but also actively penalizes unwanted generations.
Yeah.
It's designed to be efficient and doesn't require a separate reference model like PPO sometimes does.
Wow. This is where the magic really happens, where a general-purpose brain becomes a highly specialized expert. It's like a sculptor refining a masterpiece, chiseling away until every detail is perfect. But how do you know if your masterpiece is actually perfect or even good enough? That brings us to stage 5, evaluation and validation.
Exactly. Once you've sculpted your model, you need to rigorously assess its performance on unseen data. You need to check if it actually learned what you wanted it to and if it generalizes well. This is evaluation and validation. The foundation for setting up evaluation often involves metrics calculated during training, like cross-entropy. This is a fundamental loss function that measures how different the model's predictions are from the actual target outputs in the training data. It guides the learning process. Beyond that, for evaluating the final model, perplexity is a key metric. It measures how well a probability model predicts a sample, essentially. It's uncertainty or surprise about the next word in a sequence.
Lower perplexity means it's less surprised, more confident.
Exactly.
Yeah.
Lower perplexity generally indicates higher confidence and better performance in predicting the data it was trained on, or similar data. It's also vital to understand the training loss curve. This graph plots the training loss, and often the validation loss, over time, over the training epochs.
What should a good curve look like?
Ideally, you want to see a rapid decrease in loss early on, followed by a gradual decline and eventual plateau. This indicates the model is learning effectively and converging. Specific patterns can reveal issues. If the loss stays high and doesn't decrease much, the model might be underfitting. It's not complex enough or hasn't trained long enough to capture the patterns in the data. If the training loss keeps decreasing, but the validation loss starts to increase.
Ah, that's the classic sign of overfitting, right?
Precisely. The model is memorizing the training data, including its noise, but failing to generalize to new unseen examples. Wild fluctuations or spinks in the curve might indicate issues like a learning rate that's too high or noisy gradients.
And how do you fight overfitting?
Common techniques include getting more diverse training data, if possible, using data augmentation, applying regularization techniques like L2 regularization or dropout, and crucially, using early stopping the training process when the validation loss starts to rise. Monitoring and interpreting these results is an ongoing process during training and afterwards. You're looking for consistent improvement across both training and validation metrics. If they diverge, it strongly points to overfitting. You also want stability in the metrics. For more comprehensive assessment of the LLM's capabilities after training, we rely on various evaluation benchmarks. These are standardized data sets designed to test specific skills.
Like standardized tests for AIs.
Kind of, yeah. The report lists many examples. For general knowledge reasoning, benchmarks like GPQA, PhD-level questions, MMLU PRO, a refined version of a popular benchmark, ARC, AI2 Reasoning Challenge, GoBH, Big Bench hard focusing on difficult tasks, for question answering comprehension, CoQA, conversational QA, DROP-P, reasoning over paragraphs, Squad, read and comprehension, for specific tasks, text retrieval, WMT, machine translation, XNLI, cross-lingual understanding, PQA, physical common sense, Winogrand, common sense reasoning, truthful QA, checking for truthfulness hallucination, IFEVL, instruction following, math, solving math problems. Using a diverse set of relevant benchmarks gives a much broader picture of the model's strengths and weaknesses. Beyond traditional performance on these tasks, robustness evaluation is paramount, especially for real-world deployment.
This is about safety and reliability.
Exactly. It assesses the model's resilience and ethical behavior. It includes evaluating toxicity, ensuring it avoids generating harmful, offensive, or inappropriate content, stereotype bias, assessing prejudice across various demographic groups, gender, race, etc., adversarial robustness, checking its resilience against deceptive inputs designed specifically to trick the model or cause it to fail.
Like trying to break it on purpose.
Essentially, yes. Testing its defenses. Out of distribution or robustness. How well does it handle inputs that are different from the data it was trained on? For example, if it was trained on news articles, how does it handle poetry? Robustness to adversarial demonstrations. Can it be easily misled by faulty examples in the prompt? Privacy. Does it inadvertently leak sensitive information present in its training data or prompts? This leads us directly to the importance of content moderation models. These are crucial for ensuring safety and reliability, especially for LLMs that interact with the public.
Like guardrails for the AI's output.
Exactly. The report highlights specialized models developed specifically for this purpose. Llama Guard 2 and 3. These are instruction-tuned models from Meta, built on their Llama model series. Llama Guard 2 uses Llama 2 7B, while Llama Guard 3 uses Llama 3 8B and adds more safety categories like defamation and elections. They classify prompts and responses based on safety policies. Shield Gemma, an advanced model from Google built on their Gemma platform. It filters various harm types like offensive language, hate speech, and misinformation. It's scalable, with different model sizes available, and uses synthetic data generation to reduce reliance on human annotation for training. WildGuard, an open-source tool built on Mistral 7B. It addresses 3 tasks: detecting harmful intent in user prompts, identifying safety risks in model responses, and checking if the model appropriately refuses unsafe requests. It performs comparably to or even exceeds GPT-4 on some safety benchmarks. The strategic insight here is that safety isn't just a nice-to-have, it's being actively engineered into the foundation of LLMs with increasing sophistication. These moderation models act as critical safety nets.
This is where we check the report card. It's not enough for the model to just work. It has to work well, be fair, and importantly, be safe. It's like stress testing a new bridge before anyone drives on it. Once we're confident in our model's performance and safety, it's time for stage 6. Deployment, bringing the LLM to life. How do we get this powerful AI out into the world so people can actually use it?
Indeed, deployment is about making the fine-tuned LLM operational and accessible for its intended applications, getting it out there. The first major decision often revolves around cloud-based providers versus on-premises hosting. Cloud providers like AWS, Azure, Google Cloud, or specialized AI platforms often use token-based pricing for inference, which can be cost-effective for smaller scale or sporadic usage. They handle the infrastructure.
Pay as you go, kind of.
Right. However, for consistent high-volume workloads or when data privacy is paramount, an in-house or on-premises solution might be better. It requires managing your own hardware and infrastructure, but offers greater control and potentially better long-term cost savings, plus significant advantages for data privacy and security, as sensitive information stays within your own environment. Now, let's explore some key deployment strategies mentioned in the report, highlighting how different approaches address specific needs. Traditional on-premises GPU-based deployments. This is the conventional approach, using dedicated graphics processing units, GPUs, in your own data center for efficient inference.
Running it on your own servers with powerful cards.
That's exactly. While offering high control, challenges include the significant upfront hardware investment and ensuring those powerful resources are always efficiently utilized, not sitting idle during low demand. To mitigate this, strategies like load balancing across multiple GPUs and distributing the model parallelism, or data parallelism, across them are employed. The report gives an example. A large e-commerce platform handling millions of daily customer queries might use this, achieving reduced latency and improved satisfaction by efficiently distributing its AI workload across its own GPUs. An innovative approach discussed is distributed LLM torrent-style deployment and parallel forward passes.
Torrent style, like peer-to-peer file sharing.
Kind of analogous, yeah. This strategy decentralizes LLMs across multiple GPUs, potentially across different organizations, often using collaborative networks. The report mentions the Petals library as an example. It partitions the model into distinct blocks or layers, which are distributed across geographically dispersed servers. Users can connect their own GPUs, acting as both contributors, serving parts of the model, and clients, running inference. The report uses a visual analogy, figure 8.1, of restaurants, chefs, and customers to illustrate how different layers of a distributed GPT might be handled by different servers, chefs, working in parallel.
So it shares the load across many machines.
Exactly. It distributes the computational load, shares resources, and significantly reduces the financial burden on individual organizations needing to run large models. A global research consortium, for instance, might use this to analyze massive datasets collaboratively across continents. Then there's WebGPU-based deployment of LLM. This leverages a modern web standard, WebGPU, that allows web browsers to directly tap into the client's GPU power for efficient LLM inference.
So the AI runs in my browser. using my computer's graphics card.
Potentially, yes, for certain tasks, without needing any plugins or additional software installations. This means real-time language translation, code auto-completion, or even customer support chatbots can process information directly within your browser, enhancing speed and especially privacy, as data might not need to leave your machine. For example, a healthcare startup could process patient information directly in the browser using WebLM, a project enabling this, ensuring data privacy and compliance by keeping sensitive data local. Quantized LLMs are another crucial strategy for efficiency. Quantization involves reducing the model's size and computational demands by representing its internal weights and activations with fewer bits, like using 8-bit or even 4-bit integers instead of 32-bit floating point numbers.
Making the model smaller and faster.
It's exactly. The result is a smaller, faster model that consumes less memory and energy. This makes it ideal for deployment on resource-constrained environments, especially edge devices like mobile phones or IoT sensors. A tech company, for instance, could deploy advanced language models on mobile devices using quantized LLMs, enabling offline voice recognition and translation, significantly improving user experience. Finally, the report mentions VLLMs. This isn't a model type, but rather an efficient inference engine or library. VLLM is designed for highly efficient request handling in large-scale LLM deployments, particularly maximizing throughput, how many requests you can serve per second. It uses clever memory management, particularly for the KV cache.
That's the short-term memory the LLM uses during generation.
Yes. VLLM uses an algorithm called page detention to manage this KV cache much more efficiently, reducing wasted memory and allowing many requests to be batched together and processed concurrently. For instance, a content marketing agency using VLLMs as their inference backend could handle high-volume SEO-optimized content generation much more efficiently, processing multiple concurrent requests and boosting their production rate. No matter which deployment strategy you choose, several key considerations remain critical. Performance optimization is vital, focusing on minimizing latency response time for real-time applications and maximizing throughput requests per second to handle high volumes efficiently. Techniques like batching and page detention help here. Security and privacy measures, including robust data security during transit and rest, encryption, and strict access controls, are non-negotiable, especially when handling sensitive user or business data. Scalability ensures the system can gracefully handle increased workloads as user demand grows, whether by adding more servers or using cloud auto-scaling.
Flexibility allows for potential future fine-tuning or updates of the deployed model, and easy integration with existing applications and systems through APIs. And comprehensive user management, monitoring, and logging are critical for tracking usage, performance, costs, and proactively addressing issues.
This is where the rubber truly meets the road. You've built this incredible AI brain. Now, how do you get it out into the world so it can actually do something for people? It's like launching a new product, ensuring it's robust, secure, and ready for everyone to use. But the journey doesn't end with launch, does it? That leads us to stage 7, monitoring and maintenance. The long game.
It absolutely doesn't end there. In fact, monitoring and maintenance are crucial for ensuring the LLM's ongoing performance, accuracy, and reliability in a dynamic real-world environment. This isn't a one-and-done process, it's continuous. The first step is to set up initial baselines. Right after deployment, you evaluate your fine-tuned model on a comprehensive test dataset and record key performance indicators, KPIs, things like accuracy on specific tasks, latency, throughput, error rates, maybe even cost per query.
So you know what good looks like from the start.
Exactly. These serve as your reference points for all future monitoring. You need to know if performance starts to degrade over time. Then you engage in various types of monitoring on an ongoing basis. Functional monitoring. This tracks fundamental operational metrics consistently. How many requests is it getting? What are the average response times? How many tokens are being used? Important for cost. What are the overall system error rates? This gives you a high-level view of the system's health and load. Prompt monitoring. This focuses on the inputs the users are providing. You monitor things like readability, complexity, and critically, potential toxicity or misuse. You might use other LLMs as evaluators here. You also look for patterns like embedding distances from typical prompts to identify outliers, or potential adversarial attempts, malicious prompt injections, trying to bypass safety filters or extract information.
Checking what people are asking it, basically.
Yes, and how they're asking it. Response monitoring. This is about checking the LLM's actual outputs. Are they relevant to the prompt? Are they coherent or are they hallucinating? Are they staying on topic? What's the sentiment? Are they toxic? You also need to watch for prompt leakage, where the model might inadvertently reveal sensitive information that was part of its input prompt or even training data. Using metrics like embedding distance from expected responses can also help detect drift. Regular testing against benchmark evaluation datasets is key here.
And how do you know when something's actually wrong? Do you get alerts?
Yes, alerting mechanisms and thresholds are vital. You need to set carefully calibrated thresholds for your key metrics to trigger alerts when things go wrong, but without creating constant alert fatigue from false alarms. This might involve detecting when multiple metrics start to drift simultaneously, multivariate drift detection. These alerts should integrate with communication tools your team uses, like Slack or PagerDuty. Some monitoring systems can even take automated actions, like blocking problematic prompts or responses that contain detected PII, personally identifiable information, or high toxicity scores. Good monitoring platforms also offer flexibility to define custom metrics relevant to your specific application. A well-designed monitoring user interface, UI, is also pivotal for making sense of all this data. It typically features time series graphs showing how metrics change over time, allowing for trend analysis and root cause investigation. More advanced UIs might offer visualizations of embedding spaces to see how prompts or responses are clustering, helping identify shifts or anomalies. For larger organizations, these systems often allow data categorization by users, projects, or teams, and include role-based access control, RBAC, to manage who can see what.
Okay, so you're monitoring. What happens when the world changes or the model's knowledge becomes outdated? How do you update it?
That's a critical part of maintenance. Updating LLM knowledge. The world changes. New information emerges. User needs evolve. There are several approaches. Retraining methods. This involves retraining the model, either fully or partially. Periodic retraining happens at regular intervals, say, weekly or monthly, incorporating new data gathered since the last update. Trigger-based retraining is more dynamic. It monitors performance metrics, and if they fall below a certain threshold, retraining is automatically initiated.
So retrain regularly or retrain when performance drops.
Correct. Additional methods. You don't always need a full retrain. Further fine-tuning on new, targeted data can update the model for specific tasks or domains. Active learning is another approach, where the system intelligently identifies areas where the LLM is uncertain or lacks knowledge, perhaps by querying users or experts, and then uses that feedback for targeted updates. Of course, updating LLMs comes with its own key considerations. Data quality and bias are paramount again. New training data must be carefully curated and checked for bias to prevent degrading the model or introducing new problems. Computational cost. Retraining or even extensive fine-tuning is expensive. Optimizations like transfer learning, starting from a more recent base model instead from scratch, are important. Downtime. Taking the model offline for updates isn't ideal. Strategies like blue-green deployments or rolling updates are needed to ensure continuous service. Version control. Keeping track of different model versions, the data they were trained on, and their performance is essential for reproducibility and enabling quick rollbacks if an update causes issues. Looking ahead, the future of LLM updates will likely involve innovations in transfer learning, maybe meta-learning, learning to learn quickly, continued hardware improvements, and strong collaboration between academia and industry to make updates more frequent, efficient, and effective. The goal is for models to remain accurate, relevant, and valuable over their entire life cycle.
This truly isn't a set it and forget it kind of technology. It's a living system that needs constant care and feeding. It's like tending a garden. You plant the seeds, you help it grow, but then you need to continuously prune, water, and weed to keep it healthy and productive. All of this, the 7 stages, sounds incredibly complex, a massive undertaking for any single organization, especially smaller ones. But thankfully, industry has recognized this, and there are now powerful platforms and frameworks simplifying this entire fine-tuning process. #3. Industrial fine-tuning platforms and frameworks.
That's absolutely right. The complexity of the full fine-tuning pipeline we've just walked through would be daunting for many teams to build from scratch. But key players in the AI ecosystem have developed tools and managed services that really democratize access to these advanced capabilities. Companies like Hugging Face, Amazon Web Services, AWS, Microsoft Azure, and OpenAI have created platforms that significantly simplify and often automate parts of the fine-tuning process. Let's look at a few examples highlighted in the report. Hugging Face AutoTrain. This is designed to simplify fine-tuning and deployment with minimal coding. The workflow, shown in Figure 10.1, typically starts with you uploading your dataset and selecting a base model from their vast hub. AutoTrain then handles much of the data preparation and model configuration automatically. A key feature is automated hyperparameter tuning, which tries to find the best settings for you. Then the model gets fine-tuned and is ready for deployment, often via Hugging Face's own infrastructure. Best practices still emphasize starting with high-quality data and picking a suitable model.
So it automates a lot of the tricky bits.
It aims to, yes, lowering the barrier to entry.
Amazon SageMaker Jumpstart. This is a feature within the broader AWS SageMaker platform, specifically designed to expedite LLM fine-tuning within the AWS cloud environment. It provides a library of pre-built, popular foundation models, and even pre-built solutions for common tasks, allowing for quicker customization. Best practices here involve leveraging other AWS services for robust data management, like S3, and cost-effective processing within the SageMaker ecosystem.
More integrated into the AWS world.
Exactly. Amazon Bedrock. This is another AWS service, but it's positioned as a fully managed service, offering unified API access to a range of foundation models, FMs, from various top AI innovators, AI 21 Labs, Anthropic, Cohere, Meta, Mistral AI, Stability AI, plus Amazon's own Titan models.
So you get choice of models through one interface. Yes, that's the idea. And it supports private customization of these models via fine-tuning in RA, using your own data stored securely within AWS. The process is streamlined. You select your model, then use simple API calls for fine-tuning. Bedrock manages all the back-end infrastructure provisioning and management. It's built on a serverless architecture, aiming for quick, secure deployment without you needing to manage servers. OpenAI's fine-tuning API. This provides programmatic access to fine-tune OpenAI's own powerful models like GPT 3.5 or GPT 4, though options may vary. The process typically involves preparing your data in a specific format, uploading it to OpenAI, initiating the fine-tuning job via the API, which runs automatically on their infrastructure, and then deploying the resulting custom model, also accessible via their API.
Straightforward access to OpenAI models. Any downsides?
The report mentions potential limitations. Cost can be a factor, especially for large data sets or extensive tuning. Data privacy and security are considerations as you are uploading your potentially sensitive training data to OpenAI's servers. There's also the aspect of vendor lock-in and generally limited control over the granular details of the training process compared to running it yourself or using more open frameworks. Finally, NVIDIA NeMo Customizer. This is part of NVIDIA's broader NeMo framework, which is heavily focused on developing, customizing, and deploying LLMs efficiently, particularly leveraging NVIDIA's GPU hardware. Its key features, illustrated in Figure 10.3, include GPU-accelerated tools for things like data curation, NeMo Curator, advanced customization options using the NeMo Customizer microservice, supporting things like model parallelism for scaling, optimized AI inference deployment using NVIDIA Triton Inference Server, and user-friendly tools. It often integrates with best-in-class pre-trained models like Llama 2 and offers optimized RAG capabilities, NeMo Retriever, really targeting robust, scalable, enterprise-ready AI deployments.
So, more focused on the high-performance enterprise side.
That seems to be a major focus, leveraging their hardware expertise, yes.
It's amazing how these platforms are making advanced AI accessible. It's like having a specialized factory at your fingertips, allowing you to custom build AI to your exact specifications without having to build the factory yourself. But even with these incredible tools, the field is constantly evolving. What are some of the cutting-edge topics and open challenges that researchers and practitioners are grappling with today, and what does the future hold? Hashtag tag 3D, cutting-edge topics and open challenges.
The field of LLMs is certainly a living, breathing entity, always pushing boundaries. The pace of innovation is just incredible. One of the most exciting areas right now, as the report details, is multimodal LLMs. These are models that go beyond just text. They can process and understand multiple types of data. Vision language models, VLMs, for instance, are a huge area. These models learn from both images and text inputs simultaneously.
So they can see and read.
In a sense, yes. They are often generative, meaning they can produce textual descriptions or answers based on visual input. They show strong zero-shot capabilities, meaning they can often perform tasks involving images and text that they weren't explicitly trained on. Applications are vast. Think conversational AI that can discuss images you show it, systems that automatically interpret medical scans, generate captions for photos, or understand complex documents containing both text and figures. Advanced VLMs can even understand spatial attributes within images, like identifying object locations via bounding boxes or segmenting different regions.
That sounds incredibly powerful.
It really is. The report gives a fascinating case study, MedVQA, Figure 11.3, on fine-tuning multimodal LLMs, MLLMs, for visual question answering specifically in the medical domain. By combining a vision encoder, like VIT, with an LLM, like Llama 2 Chat, and using efficient fine-tuning techniques like LoRa, they achieved really impressive accuracy on answering questions about medical images, significantly surpassing even powerful general models like GPT-4V on certain types of questions. Use cases are expanding rapidly. assisting radiologists with medical diagnosis by analyzing X-rays or MRIs, creating much smarter virtual assistants that can understand voice commands while also processing visual information from cameras in a smart home, and much more. Similarly, there's growing work on audio or speech elements, sometimes called large audio models, LAMC figure 11.4. These are designed to understand and generate human language directly from audio inputs.
Taking spoken language as input.
Yes. Applications include advanced speech recognition, high-quality text-to-speech conversion, and performing natural language understanding tasks directly on spoken audio without needing a separate transcription step first. How they work often involves enhancing an LLM backbone with specialized ways to represent audio. Continuous audio signals are discretized into audio tokens, using techniques like Hubert or Wave2Vec, which the LLM can then process, often autoregressively like text tokens. Case studies mentioned include fine-tuning models like Whisper for highly accurate medical transcription by adapting them to specific terminology, using audio LLMs to help legal firms transcribe and process court proceedings, or improving customer service automation by enabling systems to understand and respond to spoken queries more naturally and effectively. Despite all these amazing breakthroughs, significant open challenges and research directions remain. Scalability issues are still paramount. Fine-tuning these massive models, especially multimodals, faces immense computational memory and data handling constraints. Continuous innovation in PFT techniques and developing more resource-efficient training methods are absolutely critical to make advanced AI accessible and practical for more researchers and organizations.
We still need bigger, faster computers, basically.
Or smarter ways to train with the computers we have, yes. Security risks are a constant concern. As models become more capable, they also become targets. Fine-tuned LLMs remain susceptible to sophisticated adversarial attacks, carefully crafted inputs designed to exploit model weaknesses and cause them to generate incorrect, biased, or harmful outputs. The report mentions the importance of frameworks like Microsoft's adversarial ML threat matrix for understanding potential attacks. Solutions involve ongoing research into adversarial training models on attack examples to make them more robust, and rigorous security audits. Accountability and transparency are crucial, especially as LLMs are deployed in high-stakes or sensitive applications. There's a growing demand for comprehensive documentation of the fine-tuning process, the data used, and the resulting model's behavior and limitations. Promoting transparency using frameworks like model cards or AI fact sheets helps build trust and ensure accountability, which is vital in areas like content moderation, financial services, or government applications.
We need to know how they were built and what they can and can't reliably do.
Exactly. The integration with emerging technologies like the Internet of Things, IoT, and edge computing presents both massive opportunities and complex challenges. On the opportunity side, we could see enhanced decision-making and automation, with LLMs analyzing vast streams of unstructured data from IoT sensors for applications like predictive maintenance in factories or optimizing traffic flow in smart cities. They can enable highly personalized user experiences through local processing on edge devices. Imagine your fitness tracker giving you tailored health recommendations processed privately on the device itself. And improved natural language understanding for smart environments, like your smart home, responding more intelligently to voice commands based on real-time sensor data about your location or activity. But there are significant challenges. Data complexity and integration from potentially billions of diverse IoT devices poses huge issues with data quality, interoperability, and preprocessing. Privacy and security are even more critical when processing potentially sensitive personal data locally on edge devices, requiring robust encryption, secure communication protocols, and careful data governance. And ensuring real-time processing and reliability with very low latency is a major hurdle for applications that require immediate responses, like autonomous vehicles or industrial control systems. These challenges directly point to key future research areas. Exploring federated learning approaches to train models collaboratively across many edge devices without centralizing sensitive data, developing more sophisticated real-time decision support systems powered by edge AI, and critically, continuing to grapple with the complex ethical and regulatory implications surrounding data ownership, algorithmic transparency, fairness, and potential societal impacts as AI becomes more deeply embedded in our physical environments and daily lives.
This isn't just about making current LLMs better. It's about pushing the boundaries of what AI can do by making it smarter, safer, and more integrated into our lives. The report calls for continuous innovation and collaboration, and that's precisely what's happening.
If we connect this to the bigger picture, what we've unpacked today really shows that fine-tuning large language models is far from being a simple single step. It's a complex, multi-stage process that demands meticulous attention, really careful consideration at each phase. From the initial curation and preparation of high-quality data, through the intricacies of model initialization and setting up the training environment correctly, then navigating the transformative fine-tuning techniques themselves, things like LoRa, DORA, mixture of experts, PPO, DPO, and in the absolutely critical stages of rigorous evaluation, using benchmarks and robustness checks, choosing responsible deployment strategies, and committing to ongoing monitoring and maintenance. This deep dive, based on that CEDAR report, has hopefully shed light on not just how these powerful models are adapted, but also the crucial distinctions between fine-tuning and ARAG, the detailed pipeline that underpins robust LLM development, the various optimization techniques that make it feasible, the vital role of evaluation and safety models in ensuring responsible AI, the diverse deployment strategies for getting LLMs into the real world, and the really exciting future unfolding with multimodal LLMs. The real power of LLMs ultimately lies not just in their sheer size, but in their remarkable ability to be meticulously tailored, specialized, and continuously improved for specific, impactful real-world applications.
That's such an important point. This knowledge helps you, our listener, understand the sophisticated AI systems you interact with daily, whether you know it or not, and how future innovations will continue to shape your experience. This isn't just theory, it's the blueprint for the next generation of intelligence systems that are becoming part of our lives. And this raises an important question for all of us to think about. Considering these rapid advancements in fine-tuning, and especially the integration of LLMs with emerging technologies like IoT and edge computing, how might these increasingly specialized and localized AI models reshape our fundamental understanding of data privacy and personal autonomy in the very near future? As AI becomes truly ubiquitous, running on our devices and our homes, understanding our context, what new responsibilities might we, as users, as developers, as a society, need to embrace as AI becomes not just intelligent, but intimately personal? Something to ponder. Thank you for joining us on the deep dive.